By the end of this, hopefully you're going to be a little bit better at solving exponential growth and decay functions, meaning we're starting from a differential equation. I don't really like the way that sounds, solving exponential growth and decay functions. It's more like solving a differential equation that's about exponential growth and decay. So we're also going to be doing some applications involving exponential growth and decay. So this is true a lot in real life. The growth rate of something is proportional to the amount of that something. It could be the number of rabbits. It could be the amount of radioactive material. And what do we mean by proportional to? Well, we mean the more of something. Well, what are the things that are proportional? The amount and the rate of change. Okay. So we get a larger rate of change, which are a larger amount of the stuff, and we get a smaller rate of change with a smaller amount of the stuff. If you've done any half-life decay sort of things in your chemistry class, that's what we're talking about. You could also think of population growth, meaning, well, what's going to have a larger growth rate? A population of 10 rabbits or a population of 100 rabbits? Well, with more rabbits, there's more population growth, the higher the growth rate, all that sort of stuff. So the calculus part of exponential growth and decay is solving a differential equation. By the end of every exponential growth and decay where the amount of stuff is proportional to population growth, we're going to get an equation you recognize, but you've done those problems in pre-calculus classes, so merely knowing what equation you're going to use really isn't appropriate on the AP calculus test. Your job is to show something using calculus. So the rate of change of the amount of stuff, dy, with respect to time, dt, is proportional to the amount of stuff. Well, if we're going to solve, we need to separate variables. dy over y is equal to k times dt. I'm a fan of rewriting twice. You'll see as you look through released problems from the AP test, separating variables is huge, and you'll lose points if you don't separate variables. In fact, not just lose points, like they'll stop grading your work. Now, normally we'd write natural log of y for the antiderivative of 1 over y, but y represents a population. So we can just say natural log of y. We know we're not going to have a negative amount of a population. I have -7 bunnies living in the meadow. I don't think so. So k is a constant. So k has the antiderivative, k times whatever variable, in this case t. And don't forget our constant of integration. So natural log of y is kt plus c. That's not that hard. Now don't forget, a solution to a differential equation is going to be y equals something. So we need to get rid of natural log. We're going to exponentiate both sides. So I'm going to say e to the power natural log of y is equal to e to the power kt plus c. So the left-hand side is very obviously y, or the amount of stuff. That's like our output variable. And then the right-hand side, I'm going to use properties of exponents to rewrite, and hopefully you'll see why in a moment. If we rewrite e to the c, e to the kt, that gives us more like the form you're used to. You might be thinking, I'm not used to any of this. I bet you've seen this before. So y is y naught when t equals 0. That's sort of a weird statement. You could say y naught, or you could say y sub 0, or just really the initial amount. And so that's going to be e to the c, e to the k times 0, because time is 0. Except for, well, anything, well, let's say a constant, e to the power of 0 is 1, which means y sub 0 is e to the c. Okay, why are you telling me this? Well, because we have an e to the c right here. So the formula, when we're done, we get the amount of something is, we replace e to the c with the initial amount, e to the kt. You may have also seen this as a pert, I think your teachers say, or something like that. So, I don't know, if you have a multiple choice problem, just jump to initial amount e to the kt, or e to the power of the rate times time. In case you need this, hey, that y on the left-hand side, that's the output variable, the amount of stuff you'd have after a time. That y sub 0, again, is the initial amount. We showed you where that came from. K is that constant, or really the growth or decay rate, and t is, of course, time. So the rate of change of y is proportional to y when time is 0, y equals 2, when time equals 2, y equals 4. What is the value of y when t equals 3? So you might be thinking, hey, I'm good to go. I see the rate of change of y is proportional to y. I'll just jump to this because I know it's correct. And, well, I guess that's not a terrible thing to think, but you're not going to get any calculus credit, because what are you going to do right now? Well, you're going to fill in when time equals 0, y equals 2, so maybe I just do 2e to the kt. Then I use my intermediate stuff. 4 is equal to 2e to the k times 2. Take natural log of both sides. And k is natural log of 2 over 2, which allows us to rewrite 2e to the natural log of 2 over 2 times time, and then just put in time equals 3, right? Well, not wrong, but not calculus. Where's the calculus involved? Well, maybe it's in your head, and you're thinking, yeah, but I don't know, I know how to do this. That's kind of your job, to show you know how to do that stuff. So I suppose there's a nice part. And that nice part is, hey, you're just going to have to do the same work again. So let's start off with translating. And that's something that will behoove you to get good at. The rate of change of y, I guess with respect to time, although it doesn't say that, is proportional. K is proportional to y. The rate of change of y over time is proportional to y. In order to get to that other thing, I just need to separate variables. So dy over y is k dt. Or the integral of 1 over y with respect to y is equal to the integral of constant with respect to time. Natural log of the population, or the amount of something. That y isn't negative, so we don't need absolute values. And then e to the natural log of y, e to the kt plus c. Y is equal to e to the c, e to the kt. Let's change colors and change gears. T equals 0, y equals 2. Means we're going to have 2 where y used to be, e to the c, e to the k times 0. Actually, let's do k times 0 that way. And so usually it's at that point where people are like, oh, I get it. That e to the c is the initial amount. Well, we said that before, but usually it makes a little more sense then. So we can rewrite 2 e to the k times t. Are we ready to substitute in time equals 3? No, we still need to figure out what k is. So that's why we're given this intermediate data point. So now we can say t equals 2, y equals 4. So 4 is equal to 2e to the k times 2. And then I've actually already done this, although I did erase it. E to the 2k, natural log of both sides, and k is equal to natural log of 2 over 2. So now we're kind of at the final version of this equation. Y is equal to 2e, let's replace k with natural log of 2 all over 2, and then times time. And then, well, that's as good as we can get without a calculator. If you want to punch that into a calculator, hey, great, go for it. I don't think that's terribly interesting, although I might be wrong. So, kind of the same problem, except for it's already telling us the rate of change of y with respect to time is negative 2 times y, or the rate of change of y over time is negative 2 times the amount of stuff. something like that. And so, a little bit different. There's going to be some calculus involved, but we're asked, our answer is going to be a time, so we're just going to have to probably use logarithms to rearrange, but that's not hard. If I want a y, I suppose I'm going to have to rearrange solve. Let's see, so dy over y is negative 2 times dt. The integral of 1 over y dy is, I'm just going to write negative 2 times the integral of dt, which means natural log. And again, I don't think we need absolute value, because it says y is 1 when t equals 0 and y is 1/2. I suppose we could have negatives in some weird world, but all positives are going to get all positives of y's. So negative 2t, don't forget that constant of integration. And so, well, maybe it makes sense, instead of exponentiating right now, let's just substitute and see if we can get our c. So y equals 1 and t equals 0 gives natural log of 1 is equal to negative 2 times 0 plus that constant. Or, oh shoot, well, natural log of 1, that's 0, is equal to 0 plus c. That constant, well, is gone. Well, that doesn't seem right. And you might be thinking, hey, is that going to be 0 e to the rt? Well, no. What did we find was 0? What we found was 0. Let's go back to this one. Was like e to the 0, right? So that's actually going to be a 1. That won't be a problem in this next part. You'll see. I think you'll see what I mean. So I'm just going to go back to this white line. Natural log of y is equal to negative 2t plus 0. Or I didn't really have to write the 0. So now I write e to the natural log of y is e to the power of negative 2t, or y is equal to e to the power of negative 2t. And so, what is the value of t for when y is 1/2? So I put, let's change colors again. I think that's a nice transition. Let y equal 1/2. Natural log of both sides. And time is natural log of 1/2 over negative 2. You can put that into a calculator. You might be thinking, hey, time isn't supposed to be negative. Well, that's not going to end up being a negative time, because natural log of 1/2 is negative as well.